We're now going to learn how to determine if a point is an ordinary or singular point of a differential equation, just like this equation shown here. The first thing that you need to do is put the differential equation in standard form. The equation written here in the green box is in standard form. To put an equation in standard form, all you have to do is divide by whatever multiplies y double prime. The classification of points then depends on p of x, that's just the function that multiplies y prime, and q of x, which is the function that multiplies y. Let's first talk about an ordinary point. A point x is equal to a is an ordinary point of the differential equation if both p of x and q of x are what's called analytic at x is equal to a. This is probably a new definition for many of you, so we're going to go over what this means. A function is analytic at a point x is equal to a if it can be written as a power series centered about x is equal to a. In particular, it has no discontinuity and does not become unbounded at x is equal to a. Let me show you some examples. A polynomial function is analytic everywhere. A rational function is analytic wherever its denominator is non-zero. And then functions like e to the x, sine x, or cosine x are analytic everywhere. You may remember in calculus finding a Taylor series for these types of functions. This next part is really important. At an ordinary point x is equal to a power series solution always exists. Now let's talk about a singular point. A point x is equal to a is a singular point of the differential equation if either p of x or q of x is not analytic at x is equal to a. In particular, x is equal to a is a singular point if p of x or q of x is undefined at x is equal to a and or p of x or q of x becomes unbounded as x approaches a. To help us understand this better, I've written down two functions. This first function has a removable discontinuity at x is equal to a, so it's undefined at x is equal to a. And then the second function, f of x is 1 over x minus a, is both undefined at x is equal to a, and it's unbounded at x is equal to a. Here's the important part. At a singular point x is equal to a power series solution is not guaranteed to exist. If a point is an ordinary point, you can find a power series solution. But if a point is a singular point, you may or may not be able to find a power series solution. Before we walk through some examples, we need to learn one more thing, and that is how to classify singular points. A singular point at x is equal to a is classified as either regular or irregular. A singular point at x is equal to a is regular if x minus a times p of x and the quantity x minus a squared times q of x are analytic at x is equal to a. Remember, p of x is the function that multiplies y prime, and q of x is the function that multiplies y. If x is equal to a is a regular singular point, then the method of Frobenius can be used to obtain at least one series solution centered at x is equal to a. And that solution looks like this. A singular point x is equal to a is irregular if x minus a times p of x or the quantity x minus a squared times q of x fails to be analytic at x is equal to a. If x is equal to a is an irregular singular point, then the method of Frobenius is not guaranteed to produce a solution. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.